Hello everyone, in this video we're going to explore the alternating series test for convergence. Alright, previously we only deal with most series that have positive terms. In this session we're going to deal with the series that has both positive and negative terms. That's called alternating series. Alright, so we look at the definition right here. An alternating series is a series either of the form this guy or this guy. For the first one, if n equals 1, we substitute over here, we have the power of 2, right? So negative 1 power of 2 is going to be 1. 1 times a sub n is going to be a sub n. So the first term is going to be positive, right? The second term, this one becomes odd number, right? So the negative 1 raised to the odd number is going to be negative, right? So the second term is going to be negative, etc. Alright, third term is positive, the fourth term is negative. Or you're going to see this guy right here, only power of n, right? The first terms become negative, right? The second terms becomes positive, right? Where a sub n positive for all integers n greater than or equal to 1, right? We're going to look at the theorem alternating series test. Let b sub n greater than or equal to 0 for all n. The alternate series a sub n where a sub n equals negative 1 to the n times b sub n, or a sub n equals negative 1 raised to the n plus 1 times b sub n. Converge if the limit of b sub n approaches 0 when n approaches infinity. Number 2, the sequence b sub n is a decreasing sequence. What does that mean? It means b sub n greater than or equal to b sub n plus 1 for all n greater than k, where k is an integer, right? Now, for the proof of this theorem, you're going to check it out in the videos 10.7a. Now, example number 1, determine if the following series converge by the alternating series test. Alright, so we look at the theorem right here. We need to verify number 1 and number 2 right here, right? So we're gonna let this one right here be b sub n, right? And the whole thing right here, I call this a sub n equals the whole thing, right? Now, number 1, we need to verify limit of b sub n when n approaches infinity equals 0, right? So we have limit of 1 over n when n approaches infinity equals 0. So this one satisfies, right? Now number 2, we're gonna verify this guy right here, right? So I have n plus 1 greater than n, right? Now I'm going to take reciprocal both sides, so I have 1 over n plus 1 less than 1 over n, right? So it's the same thing as b sub n greater than or equal to b sub n plus 1, right? Number 2 right here satisfies, right? So from these two guys right here, we can conclude that the series a sub n converges, right? By the alternating series test. Now on the AP exam, you must write this one out. Alright, so keep that in mind. Now question B. I'm gonna let the whole thing right here be a sub n, right? And then this guy right here, I'm gonna let this one be b sub n equals n over n plus 1, right? Now I need to verify number 1 right here, right? So I'm gonna take limit of n over n plus 1 when n approaches infinity. It's gonna be limit of n over n when n approaches infinity, right? Because number 1 right here doesn't really matter, right? So I'm gonna simplify this one, it's gonna be 1. This one not equal to 0, right? So you're gonna say that the alternating series test is inconclusive, right? To verify non-increasing behavior for a sequence, Number one, you can use algebraic difference test to show that a sub n plus 1 minus a sub n less than or equal to 0, right? This guy tells us that a sub n always greater than or equal to a sub n plus 1, right? Now, number two, you can use algebraic ratio test to show that a sub n plus 1 over a sub n less than or equal to 1. This one also tells us that a sub n always greater than or equal to a sub n plus 1, right? Now, number two, you can use the derivative of the related function f of s for which a sub n equals f of n for all n defined for s greater than 0 shows that the first derivative less than or equal to 0 for all n greater than k for some k in the integer set, right? Now, example number 2, determine if the following alternating series converge or diverge, right? So, I'm gonna let the whole thing right here be a sub n, right? And I'm gonna let b sub n equals 1 over 2 and altogether factorial, right? First, I need to verify if limit of b sub n when n approaches infinity equals 0, right? But b sub n equals 1 over 2 and altogether factorial, right? This one equals 0, right? Now, number 2. We're going to use the second one right here to do it, right? We're going to have b sub n plus 1 over b sub n. It's going to be 1 over 2 times n plus 1 factorial over 1 over 2 times n factorial. Now I'm going to multiply the top bottom by 2n factorial. So I'm going to end up with 2n factorial over 2 times n plus 1 factorial, right? Now I'm going to distribute the bottom, so it's going to be 2n factorial over 2n plus 2 factorial, right? So look at the bottom, it's going to be 2 units greater than the top, right? So I just write 2n factorial over 2n factorial times 2n plus 1 times 2n plus 2, right? And then this guy cancel out. It's going to be 1 over 2n plus 1 times 2n plus 2, right? And look at the bottom right here. It's going to be always greater than 1, right? So then this guy always less than 1, right? So this one tells us that b sub n is decreasing, right? So by the alternating series test, this series converges, right? Now, question B. I'm going to let this one be a sub n, right? And then b sub n equals n squared over n squared plus 25, right? Now, I'm going to go back to the alternating series test, right? I need to verify two things, right? It's going to be right here, right? So, I'm going to check to see if limit of b sub n when n approaches infinity equals 0 or not, right? So I'm going to have limit of n squared over n squared plus 25 when n approaches infinity. It's going to be limit of n squared over n squared when n approaches infinity, right? By relative growth rate when n approaches infinity, 25 doesn't really matter, right? So I can drop 25, right? So if I simplify this, could be 1, different from 0, right? Now, the first condition is not met. There's no reason for me to check the second one, right? So I can conclude that a sub n is not convergent by the alternating series test, right? Now you need to read the question carefully. The question says, determine if the following alternating series converge or diverge, right? It doesn't say that you need to use the alternating series test, right? This question different from example number 1 right here. It says, determine if the following series converge by the alternating series test. So they make you use this theorem, right? But example number 2 right here, you can use whatever theorem to verify if this alternating series converge or diverge, right? So you're not gonna stop right here, you need to do more, right? So I look at this one, I can use the n-term test. That's called divergent test. We're gonna take the limit of a sub n right here, right? So we have limit of a sub n when n approaches infinity equals limit of -1 to the n times n squared over n squared plus 25 when n approaches infinity. Now observe that this limit always equals 1, right? And then this limit right here is going to be alternating between 1 and -1, right? So obviously this limit does not exist, right? It's the same thing as limit of a sub n when n approaches infinity diverges, right? By the n-terms test. Now, let's move on to question C. I'm gonna let the whole thing right here be a sub n. And then b sub n equals square root of n over n plus 4, right? Now, I'm gonna check the first one to see if limit of b sub n when n approaches infinity equals 0 or not, right? So, I'm gonna take limit of square root of n over n plus 4 when n approaches infinity equals limit of n power of 1/2 over n when n approaches infinity, right? I can drop for by relative growth rate, right? So this one is the same thing as limit of 1 over n power of 1/2 when n approaches infinity. So it could be 0, right? So the first one is met. Now the second one, I'm gonna let f of s equals square root of s over s plus 4, right? I'm gonna use the third one right here to verify if the function is decreasing, right? Now I'm gonna check the derivative of this one using the quotient rule, right? So I have u over v prime is going to be u prime v minus v prime u over v squared, right? So it's going to be 1 over 2 square root of s, right? Times s plus 4 minus 1 times square root of s over s plus 4 altogether square, right? So it's going to be 1 over 2 square root of s times s plus 4 altogether square. Now I can put 4 minus s on the top. So in order to use the alternating series test, I need this guy to be less than or equal to 0, right? Now I need to find the critical numbers. So the critical numbers are s equals 0, so s equals 4, right? The bottom right here, square root of s equals 0, s equals 0, right? S plus 4 equals 0, s equals -4, right? But you need to be careful. You need to eliminate this one. Why? Because s for -4 makes the original one right here undefined, right? So we only have two real numbers, right? We're going to draw the number line, right? So we're going to put 0 here, 4 here, right? Now we're going to pick a value within this interval. So suppose I pick 1, right? I substitute 1 for s back over here, right? So 4 minus 1 is going to be 3. The bottom is positive. So this one positive, right? So I have the plus side right here. If this guy plus side, this guy must be negative. This guy must be negative, right? Now I need this guy to be less than or equal to 0, right? So I'm going to conclude that f prime of s less than or equal to 0 when s less than or equal to 0, right? This guy right here. Or s greater than or equal to 4, right? Now we're going to go back to original series. We're going to replace s with n, right? So we have s prime n less than or equal to 0. If n less than or equal to 0 or n greater than or equal to 4, right? S must be greater than 0, right? For some n greater than k, right? So we can eliminate this guy right here. We only take this guy, right? So p sub n is decreasing on 4 to infinity, right? This guy right here. So the second one is met, right? The first one is met. So by the alternating series test, a sub n converges, right? Now let's move on to question D. Question D is interesting. Why? Because you don't have -1 to the n or -1 to the n plus 1, right? So in order to use the alternating series test, you need these two guys, right? But this guy right here is hidden. Why? Look at this one right here. We know that cosine of pi equals -1, right? Cosine of 2 pi equals 1. Cosine of 3 pi equals -1. Cosine of 4 pi equals 1. Cosine of 0 equals 1. Alright, so technically cosine of n pi actually -1 power n, right? If n is even, it's gonna be positive. If n is odd, it's gonna be negative, right? So this series can be written as sigma when n equals to infinity of -1 to the n over square root of n, right? I'm gonna let this one be a sub n, right? And I'm gonna let b sub n be 1 over square root of n, right? Now I'm gonna check two conditions, right? The first condition, I'm gonna take the limit of b sub n when n approaches infinity. It's gonna be limit of 1 over square root of n when n approaches infinity, and this guy actually 0, right? So the first one met. Now the second condition, I have square root of n less than square root of n plus 1, right? I take reciprocal both sides, so I have 1 over square root of n greater than 1 over square root of n plus 1, right? And this guy actually b sub n, right? And this guy actually b sub n plus 1, right? So you just prove that b sub n greater than b sub n plus 1, right? So the second condition is met. So by the alternating series test, the series converges, right? And it's your time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand in mine.